Hi everyone, welcome back to Math with Amala. This part is part number 4 of grade 12, chapter 1 Relations and Functions. Here we deals with the continuous part of exercise 1.1. We deals with the question number 1 first. The first part is a is equal to 0, 1, 2, 3, etc. 12, and we have given with a relation that set of AB such that modulus of a minus b is multiple of 4. So we can define R as 4, 0, 0, 4, 5, 1, 1, 5, 6, 2, 2, 6, which means in all these elements or the members, the numbers are related like modulus of a minus b is a multiple of 4. We can take any random number, 8 and 4, 8 minus 4, modulus of 8 minus 4 or modulus of 4 minus 8 is a multiple of 4. Likewise, we can continue this and fill the relation set and we can end with the 12, 12. So x comma x, it is reflexive because modulus of 4 minus 4 is there, 8 minus 8 is there, 12 minus 12 is there, which are all equal to 0 and it is a multiple of 4, it is reflexive. Likewise, mod a minus b, b minus a are multiples of 4, hence it is symmetric. Mod a minus b and b minus a, b minus c, which implies mod a minus c. This is also a multiple of 4. We can have different examples from the set. Okay, so hence it is an equivalence relation since it contains all the three reflexive, symmetric and transitive relations. Second case is set of all AB such that A is equal to B. Here A is equal to A itself, hence it is true case, it is reflexive. A is equal to B implies B is equal to A, hence it is symmetric. Because it's the reverse also can be obviously taken for the equal to sign. Now A equal to B and B equal to C implies A equal to C. Hence it is transitive. This relation is transitive. That is, if A equal to B and B is equal to C, then we can say the first and the third are equal. Okay, hence it is an equivalence relation. Without any doubt, we can say that it is satisfying all the conditions of reflexivity, symmetricity and transitivity. Okay. Then the 10th question, we have to give some examples for the relations which are symmetric, not reflexive and transitive. So let's give the example R is equal to set of 3, 4, 4, 3 from the set 2, 3, 4, 5. It is obvious that it is only symmetric but not reflexive or transitive. Second question, transitive, it should be transitive but not reflexive and symmetric. R is equal to set of AB such that A less than B. Then we can have A less than B, B less than C implies A less than C, because let's take A and a bigger B and a bigger C. Then we can say A is less than or equal to C or less than C. Okay, the third one, it should be symmetric and reflexive but not transitive. Let's take R is equal to set of all AB such that A is a friend of B. So we can say it is reflexive because A is friend of A itself. And also A is friend of B means B is friend of A. But we can't say that if A is friend of B and B is friend of C, it doesn't mean that A is friend of C. Okay, so it's not transitive, but it is both reflexive and symmetric. Now we need another example for reflexive and transitive but not symmetric. Let us take the example of A less than or equal to B. Here A less than or equal to A, hence it is reflexive. A less than or equal to B doesn't imply B less than or equal to A. But A less than or equal to B, comma, B less than or equal to C implies A less than or equal to C. Hence transitivity and reflexivity are held and symmetric is not possible there. Next, the fifth one, symmetric and transitive but not reflexive. Let's take the relation R is equal to set of AB such that A is sister of B. A cannot be sister of that person itself, hence it is not reflexive, but it is both symmetric and transitive. We can have sisters in this loop of transitivity and symmetric. In the 11th question, we are having the set of points on the plane where P and Q are of same distance from origin. So we have the origin O and P and Q are equidistant from the origin O. Then PP. PP means the distance OP equal to OP. It is reflexive. OP is always equal to OP. It's obvious case. Trivial case. Next PQ. OP is equal to OQ and OQ equal to OP, hence it is symmetric. Now OP equal to OQ equal to OR, hence it is transitive also. Okay, hence it is an equivalence relation which is defined on the plane for the points like P, Q and R. Now the 12th question, R is equal to set of all T1 comma T2 where T1, Ti's are the triangles on the plane, T1 similar to T2. T1 and T2 are similar means their sides are in proportion. Okay, first one you can check like T1 comma T1. T1 is a triangle. It is obviously similar to that same triangle. Hence it is reflexive. Then T1 related to T2 and T2 similar to T1. Then it is symmetric. Then T1 related to T1 comma T2 related to T3 implies T1 related to T3. Let's take T1, T2, T3 like this. Then they can be related like this. Okay. Hence it is an equivalence relation. Now let's consider the triangles, right angle triangles which are given in the question with sides 3, 4, 5, 5, 12, 13 and 6, 8, 10. Okay. Now we can conclude here that the similar triangles will have sides in proportion. Two triangles are similar if corresponding sides are similar or sides are in proportion. So we can have the first and the last, the T1 and T3 are in proportion because 3 by 6 equal to 4 by 8 equal to 5 by 10 is equal to 1 by 2. Hence the T1 and T3 are related. 13th question says about a relation P1 comma P2 where P1 and P2 have same number of sides where PI's are the polygons on the plane which are having same number of sides. Polygons are the simple closed figures which are made up of line segments and starting from the triangle. Let's take P1. It is reflexive. P1 will have the same number of sides as P1 itself. If so, it is reflexive. If P1, P2 are related, then P2, P1 is related because they have the same number of sides. P1, P2 are related. P2, P3 are related. That implies P1, P2. P1, P3 are related. Hence, it is an equivalence relation. Now, let's take 3, 4, 5 as the sides of the triangle. Then is a set of right angle triangles because they are connected with 3 square plus 4 square is equal to 5 square. The hypotenuse is connected like this because it contains the Pythagoras theorem. 14th question, we are having Li such the lines R is equal to set of all L1 comma L2 such that L1 is parallel to L2. So L1 is parallel to L1. A single line is parallel to itself, hence it is reflexive. A line L1 parallel to L2 means it is parallel to the reverse. Parallel in the reverse case, it is symmetric. Likewise, L1 parallel to L2. L2 parallel to L3 means the first and the last are symmetric, transitive. Hence, there it is an equivalence relation. Now, if we take y is equal to 2x plus 4, then y is equal to mx plus c, then m equal to 2. Where m is the slope of this parallel line. So, y is equal to mx plus c. It's a line. 2x plus 4. You can take y is equal to 2x plus k where k is a real number. Question number 15 is defined on the set 1, 2, 3, 4 where r is equal to 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, 3, 2. Okay. We have 1, 1, 2, 2, 3, 3 and 4, 4 inside this relation. Hence, it is reflexive. It is reflecting towards each element. Next, 1, 2 is there and 2, 1 is not there. Hence, it is not symmetric. Let's take another number 1, 3, 3, 2 but 1, 2 is there. Okay, which means it is transitive. Hence, this relation is reflexive and transitive but not symmetric. Okay. Hence, we can choose the option number B. In the 16th question, R is equal to set of AB such that A is equal to B minus 2 where B greater than 6. We have to choose the values of A and B from the given options. We have to choose B always greater than 6. Let's take the first one. Here we have 2, 4 where 2 is equal to 4 minus 2, where 4 is not greater than 6. So the first option is not the answer. Let's take 3 comma 8. 3 is equal to 8 minus 2. It's not true. 6 comma 8, where 6 equal to 8 minus 2, 8 greater than 6. This is the answer. Thank you all for watching the video. Please be stay tuned for the part number 5.